I'm sure most, if not all of you, have seen this viral clip of this unfortunate incident. Regardless of what the NTSB decides is the final cause, it's pretty clear the tail was involved. And I thought now would be a good opportunity to start my video series on the nature of the mechanics in our very beloved form of aviation, the rotorcraft. I spent some time helping Mr. D go through a regular inspection of his MD-500, which I refer to as the Star Cycle. By the way, Star Cycle is a reference to Jeff Beck's song of the same title, and I use it because I believe the MD-500 to be the closest thing on this planet to the vibe that song conveys. I got up early on a frosty morning for this activity. The inspection process involves complete removal of the tail rotor and associated components. There are 2 pitch links on the tail rotor. They control the pitch of the blades and rotate with them around the shaft, 1 link per blade. It's one of these that came loose on that accident aircraft in California. With 1 blade uncontrolled, you can imagine that's going to put asymmetric thrust on the axle and start tearing things up. There's a few mechanical elements like a locking washer and nut that keep that tail secured to the shaft. A Jesus nut of the tail rotor, if you will. Once you take all that off, you get the raw shaft. The spline is, of course, to keep the rotor fully rotationally locked in. This, I believe, is called the pitch horn, but whatever it's called, it's an L-shaped component that pivots at the bend. 1 leg is pulled in and out with a control rod, which results in the other leg pulling the pitch links in and out. And that's how the tail feathers, the blades, are pitch controlled. Don't know what this piece is called, but it's the collar that slides in and out along the shaft. That collar holds on to the pitch links, and that pitch horn slides the collar along that shaft. Here you can see full pedal deflection from one side to the other. To answer the question, does the tail provide thrust in both directions, or is main rotor torque enough to hold it? The answer clearly is the tail provides thrust in both directions, but torque assists, so it doesn't need to apply as much thrust in that direction. Unfortunately, I missed the removal of the tail rotor drive shaft process, but here it is fully exposed. Looks a bit like an elongated submarine to me. The drive shaft is removed completely with a 90-degree tail gearbox attached. This view of the tail rotor gearbox offers some interesting insights. If we orient it as it actually goes in the helicopter, you can see the tail rotor spline on the left where the tail feathers go. This is the gearbox fluid level sight that you check before takeoff. These strands are called safety wire. The bolts they're threaded through have holes in them. The safety wire goes through the hole and then ties to adjacent bolts. This way, no bolt can back itself out during operation because the wire restrains them from turning counterclockwise. This device is ingenious in my opinion. It's very simple. Simply a magnetic pole that samples the circulating oil in the gearbox. A signal wire attaches to that pole and goes all the way up to the console. If the gearbox is grinding and flecks of metal start coming off the gears, it's obviously an early warning sign that things are not looking so good in here. Eventually, enough flecks of gear floating in the oil stick to that magnetic pole, shorting out to the case. That short shows up as the chip indicated light on the console. That's when you know something's up. You have one of these for the tail rotor and one for the main rotor. This rod sticking out, that's the push rod controlled by the pedals that connects to that L-shaped piece. And here it is fully removed. I had the privilege of contributing to the process by cleaning the muck off the drive shaft. They guided the drive shaft carefully back down the tail through a couple of internal bulkheads, making sure not to hit anything along the way. That flange end then appears back in the main compartment and has to be bolted back onto the transmission. Then all the parts are carefully reassembled in reverse order. Everything is safety wired together so the bolts can't fall out due to vibration. Interesting thing about helicopters, unlike commercial aviation with multiple systems of redundancy, a helicopter is susceptible to single points of failure, meaning if a single critical bolt falls out, it could kill you. So all these critical elements are safety wired together so they can't back themselves out of wherever they're supposed to be. And you have inspections like these to make sure they're still in flyable shape. And when everything is back in place, the tail rotor needs to be rebalanced for minimum vibration. An optical vibration detection system is strapped on, measurements taken, weights added or subtracted, and measurements taken again. Each measurement requires a full run-up of the helicopter. Mr. D hates to do these. Each run-up is a tick mark on the wear and tear of the helicopter components. Engine time, starter starts, and so on. This round of balancing took 5 runs, and that made him a little irritable. Tough work, but for me it was fun. And I learned so much. Stuff that I enjoy sharing with you guys. I hope that was useful and educational to you, and until next time, fly it like you borrowed it.
Huh? Yeah, boy.
Yeah, boy!